Hi, this video is about the learning or characterization of algebra and the common misconceptions and suggestions on how to address them. When we define algebra, the focus is on its characterizations, meaning how is it different from the other mathematical strands. Usiskin, Capert, and NCTM has each defined algebra differently. Words like conceptions, aspects, and themes are used to refer to what I meant by the characterization of algebra. The similarity in these definitions is that algebra focuses on generalization, true representation, or modeling and structure. Caroline Kieran consolidated these aspects into three main activities, which are generational or representational, where we form expressions and equations involving variables to model a problem situation. Transformational, where we manipulate these representations to solve problems or prove a conjecture. And thirdly, the global meta level, where we generalize or justify through the use of language and syntax. To just recap on each of these three activities, let's take another look at the first activity, generational activities, which involve forming of the expressions and equations that are the objects of algebra. First example, equations containing an unknown that represent problem situations, such as when 3 is added to 5 times a certain number, the sum is 38. The question here is, what is the unknown? So the unknown here is a particular number, a certain number. So let x be the number. We're assigning a variable to the unknown. And since there are two operations for this problem situation, which is addition and multiplication, so our representation for this problem situation will be 3 plus 5x equals to 38. Secondly, we have the example of expressions of generality arising from geometric patterns or numerical sequences, such as this number pattern. In this number pattern, the difference from one number to the next number is the addition of 5. As you can remember, if it increases by 5, hence we are interested at looking into the multiples of 5. Hence, our expression will involve 5n. In multiple of 5, the first term is 5. To compare that first term to this first term 3, we need to minus 2. Hence, our expression for this number pattern is 5n minus 2. And lastly, expressions of the rules governing numerical relationships, such as this conjecture, show why the sum of two consecutive numbers is always odd. So the representation here involves two consecutive numbers. Assigning the variable x as the first number, the representation for two consecutive numbers is x plus 1. Secondly, we have the transformational activities, which aim to usually solve problems in algebra or to prove or generalize a problem situation. Transformational activities include collecting like terms, using inverse operations, expanding, factorizing, and substituting. Such as solving this equation by first expanding and applying inverse operations, factorizing, simplifying involving algebraic exponentiation, rewriting numbers in a different form, and again substituting values to solve or to rewrite expression or equation. Thirdly, we have the meta level activities, which is also known as the generalization activity or the justifying activity. So this is a tool using algebra to analyze relationships to justify or prove a particular conjecture, usually with the aim to predict a particular situation. Such as show why the sum of two consecutive numbers is always odd and show that this particular triangle is right angle. Since the first one has been discussed before, the second one, we can prove that ABC is a right angle triangle by asking students to measure all the lengths of AB, BC, and AC and to put them in an equation using the Pythagoras theorem. So global method activity here refers to the justifying of why ABC is a right angle triangle with reference to the Pythagoras theorem. Transition from arithmetic to algebra. To ease the transition from being too answer focused to being rule focused, students need to develop algebraic thinking in the early stages. In other words, we need to develop algebraic thinking by explaining patterns and relationships to students. Unlike numerical expressions, algebraic expressions can represent both the process and product of a mathematical problem. At present, for example, elementary school arithmetic tends to be heavily answer-oriented and does not focus on the representation of relations. For example, in this numerical equation, 8 plus 5 is equals to blank plus 4. So the focus here can be explaining the relationship between the value on the left-hand side and the value on the right-hand side. The problem here could be confusion with the concept of equality, because equality usually means that we need to perform certain operation and it results in a particular value. The causes for misconceptions in algebra are rooted in misconceptions in arithmetic. The question mark in these examples are used as a symbol for unknowns. In these numerical examples, the unknown can be calculated. In this algebraic example, x plus y equals to 10, the expression x plus y is a group of unknowns. Finding the solution to this equation x plus y equals to 10 means that we are looking for possible values of x and y that satisfy the equation. These solutions may be written in ordered pairs such as 2, 8. The second possible cause is thinking that the solution to a mathematical operation results in only one term. This is true for any operations involving numerical terms such as 2 plus 7, but the algebraic expression 2 plus x represents a pattern by which by itself is a product or a model. The third possible cause is poor conceptualization of negative numbers. In this example, would the unknown be a number that is greater than or less than 4? Students have previously understood that addition results in a larger number. Hence, they might struggle in evaluating the value of the question mark here. The fourth possible cause results from the misconception about fractions. In addition of fractional numbers, where students added denominators without converting both fractions to have the same denominator, similarly, they might do the same with fractions with algebraic denominators, such as 1 plus x plus 1 plus y equals to 1 over x plus y. 1 over x plus 1 over y equals to 1 over x plus y, which is incorrect. Incorrect cancellation of terms in division or not reducing fractions when performing operations may result in calculation errors. The fifth possible cause has to do with term cancellation involving a variable. For example, 3x equals to 24. It is correct to divide both sides of this equation by 3, but it's incorrect to do so to apply the same concept for x squared equals to x, that is dividing each side of the equation by x. The reason is because x could be 0. Division of any terms by 0 is not allowed. Same goes for x minus 1 equals to 2 times x minus 1. So thinking that there are x minus 1 in both sides of the equation, it is okay to divide by x minus 1. But in this case, it is incorrect to divide both sides by x minus 1, as the expression x minus 1 may be 0. Next, the concept of squares and square roots. The square root of a number, such as 4, is both positive and negative 2. but the solution for square root of x equals 2 is only positive 4. Lastly, we should emphasize on how we treat expression and equation. And in this case, it is incorrect to simplify 2x plus 4 to x plus 2 without factoring out 2. So the correct expression for rewriting 2x plus 4 is 2 bracket x plus 2. Here are some common misconceptions in algebra that you need to be familiar with. Firstly, the convention of using letters as variables is that we need to italicize the letters when they are typewritten. In this example, if C and M are variables, they should be typed in italics. If they represent centimeters, then they are typed using the normal typeface. The suggestion to avoid or address this is to exclude units throughout computation and only include them at the end or in the solution. And we should also use letters thoughtfully. In the case where C and M are variables, we can write 8MC to avoid confusion. The second misconception is assigning a particular value to a particular letter, such as A equals to 1, B equals to 2, C equals to 3, and so on. Or to associate a particular number to a letter based on previous answers. So the suggestion here to avoid or to address this misconception is to provide students with multiple problems with the same variables for different numbers or solutions, or to show combinations of different possible solutions. The third common misconception is thinking that two variables cannot have the same value. In the equation 3x equals to 4 plus y, both x equals to 2 and y equals to 2 is indeed a possible solution. In order to show this, you can demonstrate that variables may have the same solution and show that the ordered pairs satisfy the given condition. Similarly, if we have x plus y equals to 10, both x equals to 5 and y equals to 5 could be a possible combination of solutions. So think about these questions. What are the effects of student misconceptions in algebra? And when you teach algebra and notice that your students have a misconception about a particular concept, what will be your best strategy? And lastly, can you explain how algebra is connected to the other mathematical strands? That's all for today. Thank you very much and thanks for watching.